Alright, hell yeah. So someone's like, hey, can you do the Pathfinder for Olympiad and JEE? So we're doing physics, you know what I mean? And multiple choice. This stuff's hard as hell. You know, you got tests and so I guess the take-home point, though, is if it says which statements are correct or in, you know what I mean, it could be all of them. And so that's the case for this one, I think. You know what I mean? I'm not going to check my answers. I'm just going to do it. But this one I was actually able to do. And I was just like, what are they trying to get at? You know, you have a path of a particle from A to B. You have a representative angle here. And then you also have an angle here. But we're just talking about the instant in time. So at a particular instant in time, cool, you have this distance from this origin. So let's just, and then I had to look up the word modulus. I was just like, well, I've heard of the modulus of elasticity. I never even knew what the modulus part was. So I looked up the term modulus, and it said a constant or an absolute value. So I mean, you know what I mean? Like this is the value of angular velocity. So it's so yeah, so a non-vector term. So modulus is the absolute value, or it's a constant. You know what I mean? So that was kind of fascinating. I guess I learned something. And then I just looked at this and I was just like, no way. You know what I mean? Don't know how to do that one. So then I just I went to this one. And I was just like, well, modulus of tangential component of acceleration. And it's just fascinating. I'd never even look at it like this. But essentially, what we want to say is just like, this goes back to, hey, what is acceleration? Acceleration is change in velocity, change in time. What's velocity? That's change in position, change in time. So anytime you're doing with polar coordinate, you can do the same thing. You can say angular. Let's not even start with angular acceleration. I think you have to start with like maybe one that you actually know. And that's angular speed is going to be your change in angle, change in time. And even a lot of people probably don't even really use it in this form because I don't know. You know, I mean, I don't know. It's just, that's what it is. And then so angular acceleration is going to be change in omega, change in time. And I mean, this is at most people's level right here. I don't think people go a step farther. Let's see if we can. Try not to make this video too long. But if we have acceleration, hey, look at this. Didn't we just have a can't we put in velocity right here? Sure. So we have a change in the change in x, change in time. See how we have a change in that? Divided by change in time. And that's this, like, I like this little caret thing because it's the same thing as saying, hey, acceleration is dv dt and velocity is dx dt. So acceleration, will put this right into there. You know what I mean? So you're going to have derivative of the derivative of x dt divided by dt. I guess at the end of the day, this is the only thing that, you know, I know. This dt goes downstairs, or you can say, hey, this dt pops right in there. And we have the derivative of the derivative of x. So we still have this divided by dt squared. So hell yeah. And so that's where you get that d squared derivative. You know, I don't even know how you even say it. That's advanced level stuff. But at least you know, like, the time value is just squared. But this is like, you know, hey, take the second derivative. And so hell yeah. So this should explain this one, because we can, instead of doing acceleration and velocity and change in time, we're going to, well, I guess, man, maybe it doesn't, but let's do it. So we're going to have angular acceleration is change in omega, change in time. We're going to say omega is change in angle, change in time. And I'm sorry, I'm not even using the d's, so let's use the d's. So we're going to go d omega, dt, and then omega is d theta dt. And see how we have this omega? You can just throw this whole equation right into there. So we're going to have angular acceleration is d omega dt, and then divided by dt. Same thing, we're going to get that d theta dt squared, so we're going to have d squared theta dt squared. Booyah. So this is going to be angular acceleration, so check mark there. Normal component of acceleration. Even this one, I was just like, well, it doesn't look like it because I see that this d theta dt, what were we saying that? That's going to be omega. So velocity times omega, is that the normal component of acceleration? It's just like, I thought I knew the normal component of acceleration is r omega squared. But then I was just like, oh yeah, you know what I mean, take a step back because what do we know? Because omega, I always say this, omega is in radians per second, and no one knows the hell what a radian is. So I say, hey, if you take radians times something normal, times the, radians times radius is always something normal. So radians per second times the radius, this gives you something normal, and that's going to be tangential velocity. Sweet. And so if they're saying this is the tangential velocity, well, that's going to be omega r. So it's going to be omega r times omega. Well, guess what? That's omega r squared, and that is the normal component of acceleration. Booyah. So modulus of normal component of acceleration is v d phi dt. So we saw that this angle was changing. Hell yeah. And again, I should have looked down here. So if we do have some sort of angular speed of the change, and that's going to be the change in this angle with respect to time. Cool. And what I said was radians per second times the radius. That gives you that tangential velocity. Hell yeah. All right, but then they want to say the normal component of acceleration is radius omega squared. So is that going to be the same case if we have a change in this angle? So this one was tricky, but I did it visually with this. Let's say I have a rigid, you know, like bookshelf type chunk of metal right here, and it's able to rotate about that point, and it's going to rotate up right here. So now the question is, if this is a 90-degree angle and then it rotates this theta, isn't this angle theta? You know what I mean? Can I prove that? I don't know. Oh, I think the best way to prove kind of stuff like this, even if it's like just visually, you're just like, well, I think so, but I don't know. There's one that's really weird where if you, I guess I'm not going to go into it. It's something like if you have like a curve of a circle, and then the tangent here is only like a half, or is it double? So, something kind of funny. So, you know what I mean? Sometimes when you do problems like that, it messes your mind where you're just like, I don't know. But at the end of the day, hell yeah, if this is phi, these angles are equal. And if we're saying, hey, this is the change in the angle used to be here, phi used to be there, you know, and then, yeah, this is going to be the change in phi, and this is going to be the change in theta. But I could do Zorro, you know what I mean? If you have something right here, just do another line parallel to this line, and you're going to come in right there. And so, hell yeah. So that means that this is the theta theta. That means that this is theta. That means that this is, well, I don't know. Hell yeah. And I think these, I don't know, I'm just going to say those are the same, and so call it. I'm sure we got pretty close to a proof. But hell yeah, so we did it there. Because so we're just saying d phi dt is equal to d theta dt, and that's omega. And that's the angular speed of this around this point. Sweet. All right, so, and now just the tricky one. It's just like, well, how the hell do we do that one? Well, you know what I mean? I was just like, well, chill it out. And because I was just like, well, if this is omega, because what is omega? Well, if we go back here, omega, if we solve for omega, that's going to be velocity divided by the radius. Okay, I see a velocity divided by radius. So at least, you know, if they're trying to trick you twice, they would just like flip those, and then you'd be like, you know. But anyway, so those are in the right locations. But now, like, what do we know about sine and cosine? Well, typically, they're going to be percentages of a whole. Well, they're going to be or they're going to be 0 or 1. They're either going to be 100%, 0%, or somewhere in between. And so, so I was just like, well, I guess. So then I was just like, well, if that's the case, then this has to be 100%. And then I was like, what's sine of what angle is equal to 1? Well, that's going to be a sine of 90. So this angle minus this angle has to be 90. And so let's try that out. So we're just going to do this, we're going to do that, and we're saying that this velocity is tangential, because if it is the path, that is the direction of the velocity. Is that right? That's messing with me, because it seems like, yeah, is the velocity always tangential, but the acceleration can be non-tangential. The acceleration can be in all sorts of directions. It can be radial, you know, or it can be, acceleration can be tangential, or normal or tangential, because it can, you know, so yeah, that's kind of fascinating. I'm kind of losing my mind on that, but I'm just going to say for sure it's tangential. What were we saying? Oh yeah, yeah, because I didn't. Like, this must be 90. You know, if this is theta, I can see that. Then I was just saying, hey, that's 90 because it's tangential velocity, and then obviously theta, this angle minus this angle, phi minus theta has to be in 90 degrees, and then so check mark on that. So yes, they're all correct in my book, and for sure we did the first one. And I thought some of these were going to be fairly easy, but you know, this is kind of the first. I don't know. You know what I mean? It's just kind of interesting how some can be easy and some can be hard. I'm sure this one is a pretty easy one, but I don't think so. I mean, it's just kind of some weird things that you have to kind of take a look at. Some geometry. So I think we did it. So thanks for joining me on this one, and that's a video.